If you've ever gotten your hands dirty with C code, you know it can get messy and fast. But what's the secret to keeping it clean, powerful, and reusable? Well, it all boils down to one absolutely fundamental building block: functions. Seriously, picture it. Without functions, your main program is just one big messy room. You're just tossing everything in there, all your variables, your loops, your logic. It's just a giant pile on the floor. It's almost impossible to find anything. And you know that feeling. You try to fix one little thing and somehow you break three others. And that's where functions come in to save the day. They are your organizational system. Think of them like drawers, each one perfectly labeled for a specific job. Need to do some math? Pop open the calculator drawer. Need to print something out? You've got a printer drawer for that. Your main room stays spotless, and you always know exactly where to go. So here's our game plan. First, we're going to talk about what functions really are using a simple analogy. Then, we'll get technical and dissect one. After that, we'll see how to properly introduce our functions to the compiler. And then we get to the main event, a classic C puzzle that has stumped beginners for decades, the mystery of the variable that just refuses to change.
At their heart, functions are basically just recipe cards for your code. Think about it. Instead of writing out the full instructions for making a sandwich every single time you want one, you just grab the recipe card, right? It's the same in code. You write a block of instructions one time, and then you can call it or run it from anywhere you want as many times as you need.
So what are the actual ingredients on one of these recipe cards? Let's pop the hood and take a look at the anatomy of a real C function. Here we go. A simple but complete function. We've called it topla, which, fun fact, is Turkish for add. And believe it or not, this one little line tells the computer everything it needs to know to do one specific job: add two numbers together. Let's break that down. First, you have the return type, which is int here. That's the function's promise. It's what it's going to give you back when it's done. Then there's the function name, topla. That's how we call it. The parameters, int a and int b, are the ingredients it needs to work. And finally, the body, everything inside those curly braces. That's the step-by-step recipe. Okay, so we've written our recipe, but before we can use it, we have to let the head chef, in this case the C compiler, know that our recipe even exists. And for that, we need something called a prototype. You see, the thing about the C compiler is that it's a very literal assistant. It reads your code from top to bottom, one line at a time. So if you suddenly try to use a function it hasn't seen yet, it just panics. A prototype is basically just a little heads up you put at the top of your file. It's a promise that says, hey, don't worry, a function that looks like this is coming later on. And now for the main event. This is the classic C puzzle that trips up just about every single new programmer. We're going to write a function, and we're going to see if it can reach out and change a variable that lives outside of it. So here's the big question I want you to think about. If you hand a variable over to a function, can that function permanently alter the original? Let's run a little experiment and find out. Okay, look closely at this code. Inside main, we create a variable a and set it to 10. Then we pass a into our try to change function. Inside that function, it takes the value, calls it x, and changes it to 20. So when the function is finished and we're back in main, what's the value of a? Is it 10 or is it 20? Have a think. And the answer is 10. What? Nothing happened to our original variable. Our function did its job. We told it to change the value, but our variable a is completely unaffected. It's like it has total amnesia about ever visiting that function. This is the mystery. We clearly told the function what to do, but the change didn't stick. So what in the world is going on here? The answer lies in one of the most fundamental rules in all of C programming. It's all about how we give information to a function. Are we handing it a copy of the data, or are we handing it the keys to the original? This slide just nails the explanation. On the left, you've got pass by value. Think of it like making a photocopy of a document. You can scribble all over the copy, highlight it, spill coffee on it. It doesn't matter. The original is safe in the filing cabinet. On the right, pass by address. This is completely different. This is like giving someone the key to the safe. They now have direct access to change that original document. And right there, that is the solution to our mystery. By default, C always uses pass by value. It's a safety feature. When we called try to change a, we didn't actually send a, we sent a photocopy of a's value. The function took its personal copy, changed it to 20, and then threw it away when it was done.
Our original A back in main was completely safe and untouched the whole time. So let's sum it up. Pass by value, the default, is safe. The original can't be changed, but it uses a bit more memory because it has to make all those copies. Pass by address is super efficient because you're working on the original data, but it means the function can change that original. And to do this, we need a special tool called a pointer, which is basically just the key we've been talking about. Now that we know about passing the key, let's go back and fix our problem. And we'll use a classic programming example to do it, swapping the values of two different variables. On the left, you can see the attempt that's doomed to fail. That function just gets copies, so it swaps the copies, and the originals stay exactly where they were. But on the right, that's the solution. You see those little asterisks, those little stars? That's the magic. That's how we tell the function, hey, don't expect a value this time. I'm sending you a key, a memory address. So how does the syntax actually work? Well, to give the key, you put an ampersand, the and symbol, in front of the variable. That just means get me the memory address of this thing. Then, to receive the key, the function's parameter uses an asterisk, star, to show that it's a pointer. It's now holding that address, and it can use that key to go back and change the original values. And just like that, mystery solved. All right, let's lock in these key takeaways. A definition is the function's recipe. A prototype is that polite heads up you give the compiler. A call is you actually running the recipe. By default, C always passes a copy to keep your original data safe. But when you absolutely need to change the original, you pass the key, its memory address, using pointers. So there you have it. You've just unlocked one of the most powerful concepts in C, the choice between handing over a safe copy or handing over a powerful key. So as you start writing your next piece of code, think about that. When do you want to protect your data, and when is it time to hand over the keys to the kingdom? I'll leave you with that.